Okay, last module, convolution and the impulse function. So these are two fairly applied math things, and they go quite well with the Laplace transform. So first is the idea of a convolution. So a convolution is an operation where you get two functions and you merge them together and you produce a third function, and that sort of expresses how the shape of one function is modified by the others. I don't know if you've seen them before, but they're used quite a lot in particularly engineering, things like computer vision, natural language processing, image processing. So here is kind of like the example that I like to think of that explains what a convolution is. So think about your body producing hormones. For example, you get insulin from your pancreas. So you're interested in how the pancreas is function, for example. So you can take blood samples, quite regularly, and that will tell you the level of insulin in the body, and then you can graph it and you get some kind of function. But that is not going to be a graph of the amount of insulin that your pancreas secretes at time t. What you've graphed is your body's insulin levels. And how much insulin is in your body depends not only on what your pancreas is excreting now, but on all the previous insulin that the pancreas has excreted. And so we know from the fundamental theorem of calculus that if you sort of like integrate a rate of change, you get the quantity itself, right? So, but there's a catch, right? Because insulin, once it's in the body, it sort of degrades, gets used up, it decays somehow, okay? So when I'm talking about one functioning model modifying another, the decay function of the insulin is modifying the insulin production from the pancreas to get how much insulin is actually in your body. And so in this case here, the f of t, the amount of insulin in your body, is a convolution of the amount of insulin that your pancreas secretes and a decay function of some kind. How are you going to model? So the typical way you model decay is by a negative exponential. And so we can see what's happening if we just do a Riemann sum to sort of approximate what the insulin in your body, right? So if we're thinking about the insulin that the pancreas is producing, that's kind of some kind of rate. Okay, it's amount of insulin per time period. Okay, so we're at time period t, so it's going to be the amount of insulin which is produced at that moment, and then it's the amount of insulin produced in the time step before that times e to the minus k. So it's been allowed to decay for one time period, plus the insulin produced in 2 steps back times e to the minus 2k, because that insulin has had a chance to decay twice, plus I 3 steps back, the insulin produced 3 steps back, times e to the minus 3k because it's had 3 chances to decay. And if you look at what that Riemann sum gives you, you can tell that the actual amount of insulin in your body is going to be the integral from when we start till the time now of the amount of insulin that the pancreas secretes times that exponential decay, but you notice that the exponential, so they're sort of going in opposite directions. Okay, insulin's may sort of going forward and the decay is going back. Okay, and so that's a convolution. And then, so for example, if you know F and you need to find I, then you would do some sort of deconvolution. And that's what those little packs that people have that give their insulin in, it has that software in it. Okay, so we can do a definition. So given two integrable functions, the convolution of f and g, which we're going to denote f star g, is defined as that integral right there. Okay, so tau is our dummy variable, so we integrate between 0 and t, f of tau times gt minus tau. Okay, the first result, that's pretty simple, is that convolution is a commutative. F star g equals g star f. And that's quite simple. You just make a substitution, say u equals t minus tau, and then you use the definition of convolution. Okay, so when tau, when tau is 0, u is t, and when tau is t, u is 0. So it flips it there, but because it's t minus tau, when you do the du d tau, you get a -1, so you get a minus du, and you flip the f and the g's. And so you see quite clearly that that thing on the right-hand side is g convolved with f. Okay, so of course the reason why we're doing it here is because it has something to do with Laplace transforms, and the Laplace transform of the convolution is the product of the Laplace transforms. Okay, so we can think of convolution, it's some sort of kind of multiplication of functions, right? So what this is basically saying is that that we have the Laplace transform is a ring homomorphism, right? Because it's linear, and it sends so if we think of the product in the normal T space as convolution, and the product in Laplace space as just normal function multiplication, then we have a ring homomorphism. And that's quite easy to show because, well, what is the Laplace transform of f convolved with g? Well, you just plug in the definitions of both the Laplace transform and convolution. So we get a double integral, and you know, when you've got a double integral, the standard thing to do is reverse the order of integration. And so when so t is tau is going from 0 to t, and then t is going from 0 to infinity. So when you reverse it, you see that tau must go to 0 into infinity, and for each tau, t goes from tau to infinity. So we can write that. We can reverse the order of integration, and when we do that, of course, the t integral is the one that's inside, so we can take out f of tau because that's a constant with respect to t. And then on the inside integral, you make the substitution u equals t minus tau. And you go ahead and do that, and e to the minus st becomes e to the minus su plus tau. So now e to the minus s tau is a constant, so you can pull that out. And you see that you've got, in the inside integral there, you've got Laplace transform of g, and outside it, you've got the Laplace transform of f. Okay, and everything's good. So that's quite straightforward to prove. So the big thing, main thing that convolution is used for in Laplace, when you're doing Laplace transforms, is it's a nice way to invert transforms. Okay, so the inverse Laplace transform of f times s is capital F times g is the convolution of little f and little g. So for example, we want to invert 1 over s plus 2 squared, right? We already know what the answer is, but we know that the inverse of 1 over s plus 2 is e to the minus 2t. So we want e to the minus 2t convolved with itself. So you just plug that into the definition. And you see that you got an e to the minus 2 tau times an e to the 2 tau, so that cancels. So you're just left with the integral of e to the minus 2t, but it's an integral with respect to tau, right? So e to the minus 2t is a constant. So its antiderivative is e to the minus 2t times tau. And then you do that between tau between t and 0, and you've got t e to the minus 2t, which we knew what that was the answer. Okay, in the last module, I mentioned the inverse Laplace transform of 1 over s squared plus 1 all squared, and just by playing around, I found what the inverse is. Say you couldn't see that. Well, what you would do is you would do sine of t convolved with sine of t. Okay, so you throw that into the definition. So you get sine of tau times sine of t minus tau. Well, the only thing now to do is do the subtraction formula for sines. And so sine of t minus tau is sine of t times cosine of tau minus sine of tau times cosine of t. Okay, now this is an integral with respect to tau, so we can pull out all the functions of t. And so we get, we're integrating sine times cosine and integrating sine squared. Okay, so the standard thing there is to note that sine times cosine is sine 2 tau divided by 2, and sine squared of tau is 1 minus cosine 2 tau on 2. So you might remember that from Calc 2. Okay, once it's in that form, it's quite straightforward then to take the antiderivative, right? So sine 2 tau on 2. So its antiderivative is minus cosine of 2 tau divided by 4. Okay, now you're evaluating that between t and 0, and so you get cosine 2t minus 1, right? Because cosine 0 is 1. So you get that there. We integrate the 1/2, we get 1/2 tau. We do that between t and 0, so we get 1/2 t. So we get minus t times cosine t divided by 2. And then we've got a cosine, we've got a minus, integrate the cosine. So the integral of that is sine of 2 tau divided by 2. And now we're evaluating between t and 0, so that becomes, we get a sine of 2t. Okay, and then, well, what's cosine of 2t? That's sine squared minus cosine squared. Okay, so we multiply that out. So the sines, cosine squared minus sine squared. So the cosine squared times sine minus sine is a minus sine times cosine squared. The minus sine squared times minus sine is a sine cubed. Okay. Minus sine t times minus 1 is sine t. And then the cosine times sine 2t, we let sine 2t equal 2 sine times cosine. Okay, so we see we have a minus sine times cosine squared plus a 2 sine times cosine squared. So that becomes a sine cubed plus sine times cos squared, or sine cubed plus sine times cos squared is sine times sine squared plus cos squared, so that's just sine. So we get a sine plus a sine is a 2 sine, divided by 4 gets us a sine t divided by 2, and we've got the minus t cosine t divided by 2. And there we get it. And that's the answer that we got last time. So this is how you would do it if you couldn't guess the answer. Okay, the other interesting thing to talk about is the Dirac delta function. It's a function. It's really a pseudo function or a generalized function or a distribution. It's another name for it. And this turns up because in quite a lot of applied problems to do with engineering or signal processing, physics, I think that's where Paul Dirac, a famous physicist, first came up with it. You want to somehow represent a point mass, a point charge, or you want to model a system where you're hitting it with a hammer or a lightning strike. And so the delta function is also known as the unit impulse function. And so the easiest way to think of this is you think you've got a series, a sequence of functions indexed by epsilon. There's 0 everywhere except on some interval they have width epsilon and height 1 epsilon. So the integral of that is going to be 1, right? Because you've got a rectangle. And then you take the limit of that as epsilon goes to 0. And you say that, you can quite reasonably say, well, that's not a function, but it's a limit of functions. And a standard thing that you do in mathematics is you like to complete your spaces. So you talk about the space of generalized functions, which is like the space of all limits of sequences of functions which converge to something. And so we define the unit impulse at time t equals c. We're going to denote it by delta t minus c. Delta of t minus c is 0 if t is not equal to c, and it's infinite if t equals c, but it's infinite in the following respect that the integral of that unit impulse is 1 on any interval that contains c. Okay. Now it follows from that if you integrate that unit impulse at time c against any function, you're going to get the value of the function at c if c is contained within that interval. So just think of Riemann sums and taking limits, and you'll see that straight away. Okay, so the interesting thing is that the Laplace transform of the unit impulse is e to the minus cs. And so this is our first Laplace transform, which kind of not dividing by s. And the proof is you just use a definition of Laplace transform. You're integrating e to the minus st against the Dirac delta function. And c has to be greater than or equal to 0, right? And you just evaluate e to the minus st at c, and so you get e to the minus cs. So the interesting thing is the transform of the derivative of u t minus c should be e to the minus cs, right? This is because, you know, what happens when you take the derivative of the Laplace transform. And this kind of implies that the Dirac delta function is the derivative of the unit step function, which is all kind of crazy because, of course, it's discontinuous there. But applied mathematicians and physicists use this for years and years and years. And then along came a mathematician called Schwartz. In 1945, he wrote this famous book, The Theory of Distributions, where he did proofs of everything and showed that this can all be made to make sense. And the second thing to note is that the Laplace transform of the Dirac delta function, or the unit impulse at time t equals 0, is 1. And so that then is the unit in our ring. Okay. Excellent. So let's have a look at an example. Here's a simple second order linear differential equation with 0 initial conditions, and we're setting it equal to delta t. So this is kind of like, if you think of this as a spring, you kind of hit it with a hammer with a unit impulse at time t equals 0, or you can think of it as an electrical circuit, and we kind of spark it, the unit impulse at time t equals 0. What's going to happen? Well, taking Laplace transforms, it's very simple, right? Laplace transform delta t is just 1, and so you just get the characteristic polynomial times x. So x is just 1 over the characteristic polynomial. We do partial fractions, and it's fairly easy to see that it's 1 over s plus 1 minus 1 over s plus 2. So that tells us that the solution to this differential equation is e to the minus t minus e to the minus 2t. Okay, so if we think of it as, we hit the spring with a hammer and it starts vibrating away, and eventually it's going to die. It's overdamped, so it's going to die like that. Now this situation where you have a system, you set it equal to the Dirac delta function with 0 initial conditions, the solution you get is called the impulse response function, and it's usually denoted h of t. And this is very easy, very useful for engineers, because say you're given a back to our system with the equation, but now we've got some kind of arbitrary forcing function f of t. You take Laplace transforms and you get x equals 1 over the characteristic polynomial times the Laplace transform of f. So taking inverse Laplace transforms, you get that the solution is going to be the convolution of the impulse response function with our input function. Okay, so this is really useful. Like, you've got some system, you don't know what the equation really is, you give it a unit impulse and you see what the response is. Usually you get numerical data, okay? You've got your numerical data, and now you want to figure out, well, what's going to happen if I do, I put in a sinusoidal wave or whatever. Well, you do this convolution, you've got data, table of numbers, so you just do a numerical integration and you can plot what the response is going to be. So just from the impulse response, you can predict what every other response is going to be. And if you have non-zero starting conditions, you can just play with this a little bit, and you can kind of see that you can figure out what's going to happen. So just from this one example, you test your system, you can predict what every other response is going to be. This is why electrical engineers like their Laplace transforms. So let's do an example of this. So let our previous system, now we're going to input e to the minus t. Okay, so we know this is going to, e to the minus t is in the homogeneous solution, so we know that we need to multiply by t, but we can just do it with this. So by the previous slide, the solution is going to be the unit impulse response, which is e to the minus t minus e to the minus 2t. We're going to convolve it with e to the minus t. We just plug it into the definition of convolution, and we just kind of multiply out. So we get e to the minus t minus e to the minus t minus tau. We then integrate with respect to tau. So e to the minus t is a constant with respect to tau, so we get e to the minus t times tau. And we've got e to the minus t minus tau. We integrate that, we get negative e to the minus t minus tau. So negative times a negative is positive, so we get that. We do it between t and 0. So we get t times e to the minus t. We get nothing when we plug in 0 in that. And then for the second term, we do plug it in t. So we get e to the minus 2t minus, and then when we plug in tau equals 0, we get e to the minus t. That's pretty simple. Again, showing you why engineers love their Laplace transforms. Okay, and that is all the material for our class.